Good, so last time I showed how to associate to a vector bundle with connection differential forms, so-called characteristic forms. So the setup is this, so we have a vector bundle on a manifold M, structure group G. And we have a connection. And now we fix an invariant polynomial on G. So P from the Lie algebra of G to either real or complex numbers is an invariant polynomial. And then what we can do is we can associate the differential form on the manifold M with these data. So then this leads to, which I called P of nabla, which with nabla denotes the connection. So this is a globally defined differential form in even degrees on a manifold with values in real or complex numbers. And it is locally given by the curvature with respect to a local trivialization. Locally it's given, so if I take this form restricted to some open subset U where a local trivialization is defined, then what I can do is I take the curvature form of my connection with respect to this local trivialization and insert the curvature matrix. It's a G-valued two form, and insert this in the polynomial. And so this gives me a globally well-defined differential form, because we checked that if you change the local trivialization, then this form will not change. And this is due to this invariance property. Now, of course, the next question will be, to what extent does, to understand to what extent this depends on the choice of connection. Because eventually what we want are invariants of the vector bundles and not of vector bundles equipped with connections. So this will be the question that we will focus on today. One remark at this point, so these characteristic forms, as they are called, they are very nicely compatible with pullbacks. So if we have another manifold and a different smooth map from M to N to M, and then what happens with the pullback? So then we can pull back both the bundle and the connection. And if we look at the corresponding form for the pullback connection, which is then a form on N, then locally at least, this is given by the corresponding formula here, and we all have already seen that the connection, so the local trivialization is also a pullback, and the curvature matrices also pull back. So then this is locally given as the pullback of the curvature matrix. And now this is a polynomial, so this just consists of wedge products and sums. And both sums and wedge products commute with pulling back. So that's the same thing as f star E of omega, which locally defines my form, my characteristic form P of nabla. So briefly, the characteristic form of the pullback bundle is the pullback of the characteristic form. So that's nice. It's called the naturality of this construction, this compatibility with pullbacks. Okay, and now in order to understand better the dependence on the choice of connection, we need to a little bit of algebraic considerations first. So we have this invariant polynomial here, So let me assume without loss of generality that it's homogeneous of some degree, because it can always be written as a sum of homogeneous polynomials, and then I can just look at each homogeneous part separately. So let P from G to K be invariant, polynomial homogeneous of degree of some degree, polynomial of degree homogeneous of degree K. And certainly I only need to look at the case K at least 1, because if K is equal to 0, then I have a homogeneous polynomial of degree 0, which is just a constant function. Okay, so let's see. And in this homogeneous case, we learned earlier that we can polarize, so we can rewrite this polynomial by linear form. Right, so there exists uniquely mu, which is multilinear, and K copies of the Lie algebra corresponding to this degree. So it's multilinear, totally symmetric, such that my polynomial, when applied to some element x, is nothing but mu with x at k times. This is this polarization. Now let's try to understand what it means for mu that P is invariant. Now, P is invariant. So this means that if I replace x by a conjugate with some element from the Lie group, I get the same result. So in terms of my multilinear form mu, this means that if I replace these x's by corresponding conjugate, I get the same result, and without conjugation. Right, so this holds for all x in the Lie algebra and for all a in the Lie group. So that's what it means by definition. And now I want to differentiate this equation with respect to a. So let me consider a family of a's. So let a, depending on some value t, it's a parameter t. So it should be a family through the identity, and then we have its derivative plus higher order terms. So that should be a curve in the group. And so then in particular x is an element of the Lie algebra, because that's the tangent space. And first of all, what happens when I invert this element? In order to see that, I look at this product, which of course is nothing but, for each t, this is nothing but the identity matrix. So if I differentiate at 0, I get 0, it's constant t. On the other hand, I can compute this using the Leibniz rule. Then what we get is, well, I get the derivative of a at t equals 0 times this one, and okay, dA dt at 0 times this one at 0, plus the other way around, and a at 0 times the derivative a2 minus 1 at 0, and so the derivative of a at 0 is just x, and a at 0 is just the identity matrix, so this is the identity matrix. And here again an identity matrix, and here I have what I want to compute for the moment. And the this is equals 0. So what I conclude from this is that the derivative of this inverted curve at 0 is given by minus x. So the multiplicative inverse gets transformed into the additive inverse after differentiation. So our Taylor expansion of the inverted element is given as identity matrix minus Tx plus higher order terms. Alright, so this is just a preliminary consideration, and now let me check what I get when I differentiate this equation, this relation up here. After inserting a of t and then differentiate. So let's see. So now I insert my a of t here, and for this I insert these Taylor expansions. So I have 1 plus tx plus higher order terms x, and now for the inverse, this gives me 1 minus tx plus higher order terms for the first slot, and similarly for the other slots, same thing. And mu is multilinear, it's linear in each slot, and so I can just expand this in each slot and sort everything by powers of t. So in order to get the constant term, t to the 0, the only thing I can do is I take the identity matrix at each slot here, for each term. And then what I have in each slot is just the matrix x. So this is the constant term. Now the linear term, the terms linear in t, how do I get those? Well, then I always have to, when I expand everything, I always have to take one linear term, and the rest has also be the constant terms. So I have to take one tx term, and all the other terms are identity matrix terms. So what does this give me? Well, for the first slot, I have the option of taking this tx term, then this gives me mu of x, that's x plays two roles here, so that should not be confused, sorry for that. Let me call these y's. Y, and these are y's too. So now, this x is correct, so that's this linear term times y times identity, and the other option for the first slot is to take the identity times y times that x, which gives me minus y times x. And for all the other slots, then I have to take always the identity term, so then I have only y's. So that's what happens when I take the tx term in the first slot, but I can do this in every slot. So the other terms are just the same, except that I have to do this in the other slots. The last term will then be this one. So in other words, and then all the other terms are of higher order than t. And now we can just compare coefficients and see that what I have here, the coefficient of the t term must vanish. So this implies 0 equals mu of, let me write this as the bracket xy plus all the way to mu y bracket xy. So that's what we conclude from this. And also mu is totally symmetric, so I cannot, for the other terms, I can push the lead bracket term to the first spot, so I get this in term for each side here. So this gives me k times mu of the lead bracket term So in other words, this term must vanish for any elements from the Lie algebra. So that's what we conclude. Now, in fact, since this expression that we have here is a polynomial expression in x and y, it will still vanish if I insert elements from this Lie algebra of matrices with coefficients in any commutative algebra. We discussed this earlier. So therefore, this term also vanishes for all x and y in A tensor G. So it's a matrices with entries in A, where A is a commutative K algebra. Where A is any commutative K algebra. All right. So, and this will be useful in a moment. So what I'm going to show now is that these forms that I have constructed here, that they are closed forms. So in particular, or in other words, they represent cohomology classes. So that's the first thing we want to observe. Opposition dp of numbers. That's important. Proof. So again, without loss of generality, this polynomial P should be homogeneous of some degree. Otherwise, I do it for each homogeneous part individually. Without loss of generality, P is homogeneous of degree K at least 1. Again, if it's of degree 0, then it's a constant function, which is the closed form. And now we can again do this polarization. So write P of x in this form as before. And now let's see what happens if I insert my curvature form. So P of omega, and I want to apply a differential to this, then this would be the differential applied to mu of omega inserted k times. Now this is a multilinear form, so this is multilinear, it's linear in each slot. If I apply, and now in each slot we have differential forms sitting. This d has to be applied element-wise, and if I have any expression of this form, I apply this in each slot, and there is no sign when I apply it to the second slot, for instance, because this is of even degree. In general, if you have a wedge product of forms and you apply d to the product, then you have to take care of these signs. But the signs only depend on the parities of the degrees. They are all even, they are all 2. So what we get from this is simply mu of d omega. So apply the d to the first one, plus, and so it goes all the way up to mu of omega. All right, and now, in order to proceed, I use the Bianchi identity, which allows me to re-express the derivative of the curvature, again in terms of curvature and convection. Only what I get is the Lie bracket of the connection form and the curvature form. So that's the Yankee identity. Okay, and now I could argue, well, then I have exactly what I have to write here. Maybe I have a lead bracket in one slot and the same element in all other slots. And that's exactly what we have here too. And so by the previous consideration, this invariance of the polynomial implies that this is 0. There is one thing we have to be careful about though. Here what I insert, these are elements of, so these are elements of an algebra tensor G, namely the algebra is the algebra of differential forms of a manifold. The algebra of differential forms is not commutative. The algebra of even degree forms is commutative, but here I have one guy which is not even. So we have to be a bit careful about this. So if this was even, then I would be done at this point. But it's not really a problem, and basically the reason why it's not a problem is because there's only one odd guy, and when you commute it with any other term, it's still no sign, because all the other terms are even. So that's essentially the reason. Let me make this more precise. So let's see what happens. So after all, the whole thing is a differential form, not a matrix of differential forms. It's just a differential form. And I want to see that each of these terms is 0, and I check this by inserting vectors. Right. So let me do that. So what's the degree of this form? How many vectors do I have to insert in order to get a number? Ah, yes, sorry, yeah. Thanks. Yes, this affects the degree. So what's the degree? x1 all the way up to, so I insert tangent vectors now, 2k plus 1. So that's of degree 3. Okay, so let's see what we get. Because then this will just be a number, and we want to check that this number is 0. And well, how do I insert vectors in wedge products or sums of wedge products? So I could say I insert them into the individual components, but in all possible orders, right? So I have to sum over the symmetric group of 2k plus 1 entries, and then I insert these vectors in the individual forms. So now this is the Lie bracket of matrices. Right? And so on. I have to normalize by the number of these commutations, which is 2. And there, I forgot something. Of course, I need to take the sign into account. All right, and now let's see. Now what I'm going to do is I'm going to look at each case of the first slot separately. So I want to check which of your vectors is being plugged into this little omega thing. So that gives me 2k plus 1 possibilities. And then I have mu of the Lie bracket, and here I have xl. So I'm looking at the case sigma of 1 being L. And L then takes all the possibilities here. And then the remaining ones are still polluted. And so this comes with, okay, this has now permutations tau on only 2k slots, and the rest is then the remaining ones. Well, actually, it's a bit, it's not so easy to write down because now, of course, the else one is not included here. Maybe I write this tau 1, 2, all the permutations, but under the requirement that tau 1 equals L. And then I could also call it somehow as before. Yes. And the signum not to forget. And okay, the rest remains unchanged. And now, so what I want to do is, now the rest again, I want to again write now as a 2K form applied to these remaining vectors here. Right? So I have the sum, and well, then I will write this as mu of omega is L, and then capital omega applied to the remaining vectors, so that is x1 all the way up to x2k plus 1, but I do leave out xl, so that one is skipped. And so then, but I have to check these signs. This amounts to a sign that now depends just on L. So for the first one it's +1, then it's -1, +1, and so forth. And the normalization factor comes back. So this time each summand is being summed over permutations of only 2k terms. So this gets a 2 term. And now so that's fine, because now what we see after plugging in this vector, now this is just an element of k, so it's a 0 form of values in G. Whereas this one are 2 forms of values in G. So now everything is in a commutative algebra. So this term is 0. By this observation here, where you use as your algebra the algebra of even forms at a certain point in this case. Okay. So after all, it is okay. So this is the first one, but the other ones are just the same. Good. So this proves that these characteristic forms are closed, and so they represent homology classes. And these are the characteristic classes. Represents a homology class, which I may for which I may use these brackets as usual, but I call this then P of the bundle, to be justified later, and that's an element now in even the RAM cohomology with coefficients in R or C. So this is the RAM cohomology. We will always consider the RAM cohomology. And so P of F is called the characteristic class. That's the cohomology class. The characteristic class of the bundle F, and with respect to this polynomial, corresponding to this polynomial P. We saw already examples, namely the Chern characteristic forms. And now we have the classes, which are the famous Chern classes. So we call that the Chern class was defined as, well, I can look at the total Chern class. Right, like that. So the Chern class was given as identity plus and then a normalization factor of 2 pi I times the curvature matrix. So that is the polynomial in this case. It's an invariant polynomial. It's not homogeneous, but it splits. Yeah. And this one now represents the total Chern class of my bundle. And if I divide this up, or if I split this into homogeneous parts, then so the 0 degree part is just given by the determinant of the identity matrix, which is 1 plus, and then the other ones are called C1 of f, etc. And note that since the curvature is of even of degree 2, this is an element in H2. This is an element in H4 and so on. So these are the individual Chern classes, and the complete thing is the total Chern class. And now the notation that I'm using here suggests that this cohomology class should not depend on the choice of connection, because I have removed the connection from the notation. This needs justification, of course. So the corresponding characteristic form definitely does depend on the choice of connection. So that's our next aim. We want to see that after passing to the Ram homology class, our thing becomes independent of the choice of connection. Okay, and how do we do that? So what do we have to do actually? When do two closed forms represent the same Ram homology class? Yes, exactly. So somehow if we have two connections, I have to come up with a exact, so I have to show that the difference of the corresponding P of nablas, that this difference is exact. So I have to come up with something whose exterior derivative gives me the difference of the two things. And in fact, for this, it's very useful to have what's known in the homotopy formula for differential forms. Proposition. Homotopy formula for differential forms. And it says this, so the operator for the operator, the linear operator, Q, which maps k plus 1 forms on the manifold cross interval to k forms on the manifold itself. M is any manifold. And this linear operator is given as follows, given by, so what does the operator do? So this this variable in this unit interval I denote by t. And so what can I do? So I take a k plus 1 form, let's say, let me call it eta, That's a k+1 form on M cross interval. And I first insert into this the vector field ddt, which lives on this product manifold. So ddt is inserted into this. I use this notation. It just means that I take this k+1 form and insert this vector field in the first slot. And then the result will be a k form, because the other slots are still open. So that is a k form, but it's still a k form on M across the interval. Use notation here. So we have M across this interval, so let me call the projection map to M, obviously projection map by pi. But on the other hand, we also have inclusion maps JT from the opposite direction. We're just putting M on the slice for this time t, which is given as x is being mapped to x comma t. So this is an injection map for each t. That map. And so I have this I have now this k form on this product manifold, and I can pull it back using this map for each jt to give me a k form on M. So let's do that. Now I have a k form on M. In fact, I have a whole family of k forms on M, right? Because for each value of t, I get a k form on M. And so I integrate this over t. That's my Q of t. So that's the operator. And what does it do? Well, for this operator, we have that dq plus qd is equal to j1 star minus j0 star. So this is what I'm saying here. So this d increases degree by 1, the q decreases the degree by 1. So the complete thing preserves degree here too. So that's a degree preserving map. However, it's a map from the manifold M cross interval to the manifold M, right? In both cases. And these pullbacks are also the same thing. So they are also pulling back forms on this product to forms on M. So syntactically, the thing makes sense. Good. So that's the homotopy formula for differential frames. Let me prove it and then say something about applications. So is the construction of this operator Q clear? Yeah. Good. And so I do the computation in local coordinates. And in fact, I do it in local coordinates of M. And in addition, I have this coordinate t. And because this integral always fixes the point in M when I do the integration. So I can do this. So I can fix a point in the manifold M, and then the integration will be along the corresponding t ray here. So it's no problem to do this in local coordinates. Otherwise, if you integrate, it's always a bit tricky when you want to do things in local coordinates, because integration is a global operation and your chart may not cover everything, etc. But here it's not a problem because the point in M is fixed when you do this integration. So choose local coordinates. x1 up to xn of M. And then, of course, you obtain local coordinates by adding this t variable of the manifold M cross interval. Maybe I'd like to abbreviate this by calling it M hat. Now on. So, and now let's see what does this operator here do to a form if I express it in local coordinates. So if I start with the k form on M hat, then I can write it in these local coordinates. 2, so I write it like this. I take the sum, certain coefficient functions, omega I times what I call dxi, and that's notation that you certainly know. So here, these i's are multi-indices, increasing multi-indices, and these are the coefficients, and the dxi stands for dxi1, and so on, dxi k. Right? And since it's a k form, k is indeed the length, so I sum over such multi-indices of lengths. That's one thing, but this is the part of the form that does not contain a dt factor. Right? It's a form on m hat, and that also has this t direction. So there's another contribution, and here I sum over all multi-indices j, and then I get something of the form dt wedge dxj with certain coefficients in front of that. And here this has only length k minus 1, because we have this additional dt to get length k. So this is just the general expression of such a form involving these local coordinates. All right, good. Now I want to check this formula here, and so I compute the term qd of omega. So this omega has nothing to do with the connection form, of course, right? It's just a form. It's only a valid variable within the proof. Okay. So let's see. I want to compute this term and apply it to omega, so I first have to apply the differential to it. And if I apply the exterior differential to it, then I get something here. So I get the derivatives of this coefficient function. So with respect to the t variable, which gives me a dt, wedge dx y. Plus, so there can also be derivatives in the other x directions. So then I get a double sum. Then I have to take a coefficient function and differentiate in the direction in the direction L, and then I get a dxL here. So this is what I get from the first part. I just have separated the terms that come from the t derivative and all of the other derivatives. And then I also have to look at this part. But when I look at this part and I look at the t derivative, this does not contribute because this would give me another dt, and then would wedge with the already present dt, which would give me 0. So the second term only has a contribution like this one. And no, unfortunately, there's no space to add it. Plus, and what is the contribution? It's also sum L equals 1 to n, sum over j of length k minus 1, and then d omega j dxl, dxl wedge dxj. Sorry, I forgot the t. The t is missing, sorry. Getting too little space here. dxl wedge dt wedge dxj. Yes, well, so you follow this line. I think you can, you understand, right? Good. So that's this differential. Now I want to apply q to it. So let's do that. So the first, when I want to apply q to it, the first thing I have to do is I have to put in the dt vector field in the first slot. This actually simplifies things. So let's do that. What do we get if I put in this field in the first slot, looking at this local expression. When I take the first one, I put in the dt in the first slot. This exactly hits the dt as it should, so this would give me 1. So this just removes this dt factor here. So what I get is sum I equals k omega I d omega I dt times dxi. So that's what I get for the first term, because slotting in the ddt field removes the dt factor. The second one gives me 0 because it doesn't have a dt factor. So this goes away. And the third one is similar to the first one, except that there's an interchange of dx and dt. So I have to first interchange it and then remove the dt, which gives me an additional sign. So what I have is minus sum over L, sum over j of length minus 1. And then I have these derivatives, d omega j, dxl, and then dxl wedge dxj. So that's what I get from that. And now let's apply q. So I have to pull it back to the original manifold m, and then integrate against t. And if I do that, well, in local coordinates, actually, this pulling back via jt does not change anything, because whether I consider this as coordinates on m or on m hat, I use the same coordinates anyway, right? So the same symbol for that anyway. So q of d omega is now integral of what? So I do this with all these terms. So let's start with the first one. I can also pull out the sum. And I have to integrate the coefficient that I get here against t times, this gives me a number, and this is now the form that I get from this, minus this double sum, and also here I have to integrate this coefficient, which gives me a number, which is then the coefficient of this new form. So that's what we have. And now, let's see. This first one is of course great, because I take this coefficient, differentiate it, and integrate it again. So this cries for a theorem from first semester, fundamental theorem of calculus. So indeed, so what we get is now this coefficient evaluated at 1 minus the coefficient evaluated at 0 times dxi. So that's the first thing. And for the second, that's correct. Thank you. You saved me from getting confused. Thanks. Yes, indeed. So, and here I have a t integration, but an xl differentiation. So in this case, no fundamental theorem of calculus. But what I can do is I can interchange this integration with the differentiation here, because everything here. So this is an integration over a compact interval. Everything is smooth, so I can interchange integration and differentiation. And I also interchange these two sums. And I have dxl applied to the integral of omega j dt dxl, and the whole thing wedge dxj. Okay. Now what do we have here? Well, here I have to insert the value 1 into my coefficient and take the matrix. This is of course nothing but pulling back the form with J1. So, because what does this pulling back with J1? If I pull back a form from M hat to M with J1, what does it do? It kills all the dt parts and inserts the value t equals 1 into the coefficient. And that's exactly what we have here, because if you look at what how omega looks like, it's this form, the dd part is killed, and in this part we insert the value of 1. So this one is nothing but J1 star of omega. And similarly, this one is J0 star of omega. And now what we have here? Well, here we differentiate our coefficient functions in direction xl and then add a dxl in front of the other dx's. So this is exactly differentiation, exterior differentiation of what? Of the integrated differential form, where we have removed the dt parts. And indeed, if we look, so if we first apply q, if we take this form omega and first apply q, then we have to, then this term drops. Here we have to remove the dt, and we have to integrate the coefficients. This is the definition of the q. So the q applied to omega will be the sum over the j's, and then the sum over the j's, and then this one removed, so these ones integrated and times these dxj's. If you take the exterior derivative to it, then this is exactly what you get here. And that's the proof. And such a thing is called a chain homotopy in algebraic topology. And the reason why this is usually derived is because it shows that in the Ram cohomology, homotopic maps give rise to the same map on cohomology. So we briefly indicate that before we return to our bundles. And that's why also it's called the homotopy formula. So as a corollary, we see that if F0 and F1 from a manifold M to a manifold M are homotopic smooth maps, then the pullback maps on cohomology for F0 and for F1, so these are pullback maps from the cohomology of M to the cohomology of N, they coincide, they are the same. Homotopic maps give rise to the same map of cohomology. Why is that? Well, once we have this homotopy formula, that's very easy to see. To be homotopic, what does this mean? This means I can smoothly deform F0 into F1, and I can consider this as a map defined on n hat, m cross interval. So F and F0 and F1 homotopic means that there exists F, capital F, on n hat, which is n cross interval to m, such that F restricted to 0 here. So F restricted to 0, but I can write this as compose with J0 as F0 and F composed with J1 as F1. Like that. These are these embeddings of M at the left and the right end of the interval. And so composing with this inclusion just means I restrict F to the left or to the right interval. And one gives me the map F0 and the other one gives me the map F1. So that's what it means to be homotopy. And now, so let's see, if I apply this to a cohomology class, or I apply that one to a cohomology class, this means I So pullback on form on cohomology classes is defined by pulling back the representing forms. So that is f0 omega minus f1 star omega. And now so now f0 is the composition of capital F and J0. And similarly for the other one. So this is a contravariant factor here. This looks like this. And now we are in the realm of this homotopy formula, because I have a difference of J1 upper star and J0 upper star, and I apply it to the capital F star omega. So by homotopy formula, this can be rewritten as dq F star omega minus q d F star omega. However, if exterior differential and pullback commutes, so this is the same as F star d omega, but omega represents a cohomology class, so it's closed. So that means d omega is 0. So that is 0. So this term goes away, and we are just left with this other term, but that is an exact form. So the corresponding cohomology class is 0. So this shows this homotopy invariance of the map on the RAM cohomology. All right. So, but for us, this will be also useful, because we also want to show that the difference between two closed forms is exact, and we can use that for our purposes too. So let me do this now. So let's go back to bundles. So F is a vector bundle over M. The structure group G. And two connections. And I have the associated covariant derivatives. I denote by nabla 0 and nabla 1. I'm going to work with those and their associated connection forms. So I have now a bundle with two connections, and I have a homogeneous polynomial, invariant polynomial. E from G, okay, invariant polynomial. So what we now do is we look again at this manifold M hat, which is given as M cross interval, as before. I still have this projection pi into M, and now I can, and also these inclusions JT, and what I can do is I can pull back the bundle and also both connections to M hat. Pull back. So I put F hat to be the pullback of the bundle F onto the manifold M hat, and the connections too. okay, sorry. So far, nothing much has happened. I've just pulled back everything to m cross the interval. But now I will take these two connections which I have on m hat and produce something out of the third connection on m hat out of these. And this only works on m hat and not on m itself. Namely, define third connection on this pullback bundle by interpolation between these two. Namely, this is as follows. I really take 1 minus t times 0, right? Plus minus t times. Just check that I did it the same so that I don't plus. So plus of what? 1. Yes. So this is again a covariant derivative, has all the properties of covariant derivative. So it defines parallel transport defines horizontal spaces. So this defines a third connection on my bundle F. And I'm going to work with this one. And why is this of interest? Well, it's of interest because if I go back to the manifold M, and I can do this by pulling back via these inclusion maps, then we'll see that J0 star of omega hat. So that's again a connection on the original bundle. And which one is it? Well, it's just omega 0, because what we essentially do is, so this one, this covariant derivative, I have to insert t equals 0 here. So this gives me nabla 0, and when pulling back, the dt derivative just gets removed again. So this gives me back the original connection nabla 0, and similarly for J1. So this new connection nabla hat has the property that when I pull back from one side of the interval, I get nabla 0, and from the other side, I get nabla 1. So it's not really important that I take this particular form of connection nabla hat here. I could take anything that connects these two connections, nabla 0 and nabla 1, through in a convex way here. So it doesn't have to be the function t here. You can use other functions of t too. But that's not important. Anyway, so good. So that's what's important. All right. Now, what can we say about the connection forms? So the connection form of omega I. So that's with respect to some local generalization. So I equal 1 or 0 or 1. So that's obtained by pulling back the connection form of omega hat, right? And the connection, what's the connection form of omega hat? Well, how do we get the connection form? We take sections and then we apply our covariant derivative to it, and then we express it in terms of these basis sections again. But if I have this linear combination, if nabla is defined as this convex combination, then of course the corresponding entries in the connection matrix are also the corresponding convex combination. So what I have here is 1 minus t connection matrix 0 plus t connection matrix of 1. So that's what we have. And so that's linear, so I have 1 minus t times ji star. Maybe I do it with 0 first, and the case 1 is similar. So if I do it with 0, then I have to, when pulling back, then I have to insert the value t equals 0 here. So this removes this one, but this one stays then. So then I get 1 minus 0 times omega 0 star, and but this one is obtained by pulling back the original curvature form from the manifold M, right? Remember, the hatted covariant derivatives were obtained by covariant derivatives on M originally, by pulling back along pi. So that is pi composed with J0 omega star, but this is the identity. First embed and project back gives you the identity. So this is omega 0. And similarly, sorry, what did I want to say? So this is what I wanted to say. Yeah. And similarly, if you do it with J1, the point is simply that you have to insert the value that you have here into this T coefficient here. And then you get, similarly, you get omega 1. Okay. And so this then justifies these equations, right? So this is because so the connection forms pull back, and so the connections themselves pull back. All right. Good. And and similarly for the curvatures, right? We know that the curvatures pull back to that, or we already know. So that means that J I star capital omega hat will give us omega r, the curvature of the corresponding connection. So now, after these formalities, let's apply the homotopy formula. Okay, so what do we get? Well, I'll compare the characteristic forms corresponding to these two connections. Then they are defined as given inserting the corresponding curvature matrices into P. And from this I can use this formula. So this is P of J1 star omega hat minus P of J0 star omega hat. So P commutes with pulling back, so this is J1 star P omega hat minus J0 star P omega hat. And now we are again here in the situation of the homotopy formula, where I apply the homotopy formula to P of omega hat. So to do that, and I have dq P omega hat minus qd P of omega hat. But we have already shown earlier that these characteristic forms are closed, so this guy is 0. And so the only thing that survives is dq P of omega hat, and that's an exact form. So it's a very similar argument to this homotopy invariance in the Rhine cohomology. So, as a consequence, we see that the characteristic, P of the bundle F, which is defined as the Rhine cohomology class of P of some connection, and Rhine cohomology is independent of connection. So it's an invariant really of the bundle itself and nothing else. Good. So whenever we have such a polynomial, there's a corresponding invariant of vector bundles. The polynomial has to be an invariant polynomial on a Lie group G. Then this can be used for vector bundles with structure group G. And the examples that we know already are the Chern classes. So now in particular we know that the Chern classes of complex vector bundles do not depend on the choice of connection. Alright, good. In fact, sometimes it's important also to know something about this form whose differential gives me the difference between the two. So that is something which depends on two connections. And this is known as the transgression class form. Maybe definition here. Definition QP omega hat, which I would omega hat. Actually, nabla hat is better because this is then globally defined. So this form, which I will apply to TP of the two connections. So this is called transgression form. And one has to understand this one a bit better in case one wants to work with manifolds with boundary, because then this leads to a boundary contribution, and also in the case of secondary invariance, where one wants to have finer understanding of bundles for those where the primary two characteristic classes that I've just constructed here are trivial. Okay, so we'll see that later. Yeah, maybe I should say that this lives, so this lies in A, and now if this is of degree K, then this form here gives you a 2K form, and applying the Q gives you a 2K minus 1 form. 2K minus 1 form on M, real or complex element. Okay. In order to compute this more explicitly, we would see how actually this curvature omega hat looks like of this interpolated connection. So let's do this computation because it's not terribly hard. So let's see if we can compute the curvature of this interpolated connection. We can use this doing the structure equations. Lots of hats on the board now. And okay, so let's insert the formula. Is it still there somewhere? That's the corresponding formula to this one, right? This is what we used here. So this convex combination 1 minus t omega 0 hat plus t omega 1 hat minus the thing squared. Which the same thing again. Alright, good. So what do we get? So we have to differentiate this one. But there's also now the differential of t here, right? So here we are doing, so this is a computation on m hat, where we have the t direction. So we have to take this t derivative into account. So this gives me a minus dt which omega 0 hat coming from this derivative, and then here we have plus t d omega 1 hat, and then plus dt wedge omega 1 hat comes from this t derivative. So that's what I get from the first contribution. And the second one, well, then I have, let's see, minus, and now let's see, I have minus 1 minus t squared omega 0 hat omega 0 hat, so it's this term times this term. Then I have this term times that term, 1 minus t omega 0 hat which omega 1 hat. Then I have this term times that term, so that's t 1 minus t omega 1 hat which omega 0 hat. And then I have this square, which is t squared omega 1 hat which omega 1 hat. Looks like this is all the terms. Okay, so now here I want to turn this into curvature of omega 0 again. And so what I have, so I would need the differential in order, so let's see, this is what I want to have. But then this term is missing, so I have to add it again. So I have to add the square term times 1 minus t. But I also have the square term here, but the coefficient is not 1 minus t, it's 1 minus t squared. So what I have to take is 1 minus t minus 1 minus t squared times this. This is what remains. So what is it? So 1 minus t minus 1 minus t squared. Well, this is 1 minus t times 1 minus 1 minus t. So it's t times 1 minus t. Hopefully. And in fact, it's the same coefficient that comes up here, and also the same that comes up here. So let me maybe collect those terms. So here I'm omega 0, omega 0. That's what results from here. Then I have this term plus this term. And let's see, then the next thing is this one. Here I would like to have t times omega 1 hat. But then what's missing is t times this square, which I have to combine with this guy here. So I have to add t times the square minus, so I have to add t and subtract t squared, which is t times 1 minus t, which is this one. Ah, good. That's that. So what's still missing? So I have this term, I have this term, I have all those terms, and only these two terms containing a dt are still missing. So what we have is dt wedge omega 1 minus omega 0. Okay, so let's see. Yeah, that's true. Very good. So let's see, where else did I make the mistake? So here these are, here it's all correct, right? Because the minus is outside. And here we noticed that we obtained what? So let's see. I had to add t times the thing, and I have to subtract t squared, so that's t1 minus t. And if I have a minus sign here, then you are saying then I should have a minus sign here too. Okay. Or maybe let's do it this way. Do it this way, okay? It's also fine. Yeah, thanks. That's good, because I want to slightly rewrite it. As now, here, that's it. So I want to write this as, let's see, omega 1 hat minus omega 0 hat wedge the same thing again. So this times this gives that, this times this gives this times this, this times this gets as a minus sign gives this one, and this times it also as a minus sign gives this one. So now we can write it in this form. So that we again have this difference of connection forms like here. Okay, good. So that is the curvature form of this interpolated connection on M hat. I want to apply Q to it. So the first thing I have to do is, or rather I want to insert this into the polynomial and then apply Q to it. Oh, no, I still have 5 minutes. So P of omega hat. Now this, of course, I have to just insert this k times. And so I have this interpolation of the two curvatures plus these correction terms. And so this, maybe I apply Q in order to, and then I want to apply Q to it. And for that, I have to insert dt to it, right? So that is inserting dt into, let me write this again with my multilinear form, omega hat k times. And now what happens if I do that? So there is only one part which can survive insertion of a dt here, namely this one. This is the only contribution which contains a dt. But when I insert this into this polynomial, of course, I have to insert it once here, and then another contribution where I insert it the second one, etc. And finally the last one. And so if I insert it in the first one, this means I get mu, and then only this term survives. And the other terms are unaffected. Right? And then similarly for the other sorts. And so on. So that's what I get. And the polynomial mu, or this multilinear for mu, is totally symmetric. And so in fact I get k times this first contribution. So that is that thing. The next thing is now we have to pull back to the manifold M and integrate against T. Need it more. So if we now apply this JT star to it and integrate, well, if I apply JT star to it, then I get here I get the omega 1, and here without the hat, and here I get the omega 0 without the hat. And here I get the, I have here when applying GT star to it. So maybe I should, let me write this whole thing as this contribution plus all the rest, so this convex combination of curvatures and this quadratic term here. And if I apply JT star to this contribution, so it's this part plus this part, or this part. If I apply it to this, let me call this omega t. So this is on the manifold M, but depends on T. And that's what we get when we have to integrate here. So this is k times mu omega 1 minus omega 0, and then omega t integrated against. So this is in fact, so this is our transgression form. So this can be completely computed out of the curvature forms of omega 1 and omega 2 and the connection forms of omega 2. So omega t is just obtained from this term by removing the heads. So that's a more explicit formula for transgression form. Okay, or sign mistake here anyway? No. Yeah, so now we have seen that indeed characteristic classes are independent, so the cohomology classes are independent of the choice of connection. They are invariants really of the bundle itself. And so next time we will see if we can use this somehow to check if a bundle is non-trivial, that sort of thing. Because it will turn out if the bundle is trivial, then these cohomology classes will be trivial, and so conversely, if you can manage to compute a cohomology class, it turns out to be non-trivial, you know that the corresponding bundle is non-trivial, and that's always the difficult thing to show, right? You have a bundle, and you want to show it's non-trivial. That relates, for example, to the hedgehog, or to this hairy ball theorem, and you want to show a non-triviality of a bundle. That's always the difficult thing. And these characteristic classes that we have now constructed can help you to do that. They are invariants that can help you doing this. But we'll do this next time. Thank you.